All right, Zach, Sam, Kevin, Theo, Hayden, Alicia, Elsa, Jules, Romy, Finley, Alan, Cameron, Ray, Karina, Giselle, Shiny. All right. Adriana, there you are, sorry. Shining. Stephanie, Albert, 21, 3, 8. Perfect, ladies and gentlemen, perfect. All right, so it's good to see you, ladies and gentlemen. You got a rarity, which is I got to take a day off yesterday. That doesn't happen very often, so as much as Jules enjoyed yesterday, it probably isn't going to happen again for a very long time. So let's begin with questions you have about the stuff that was either in the video yesterday, your lab, things of that nature. So, shoot. Okay, that makes life very easy then, ladies and gentlemen. I will quickly go through those slides with you that the video was on yesterday. I'm not going to spend a lot of time on them because, again, I just asked if you had questions, if there was anything about them you did not understand. I didn't change the due date in Canvas, but you turn this in by the end of the hour today and it will not be considered late. So it was supposed to be yesterday. I wasn't here yesterday. I just asked if anyone had questions. Nobody had any. So there's no reason this can't be turned in by the end of this hour today to not be counted as late. So please make sure you get that turned in time. Okay? Friday, ladies and gentlemen, maybe Thursday. I'm going to look at it, but we'll have our first quiz. So the topics will be graphing, kinetic and potential energy, heat versus temperature, maybe KMT, maybe not. But we're probably looking at the end of this week for that quiz. So today you're going to be able to show understanding of kinetic and potential energy and understanding of the concept of kinetic molecular theory. Your success in this class is determined by how much you are willing to do. Okay? Again, if you have questions, if there are things that you do not understand, I can help you with them, but not if you never ask. Not if you never come and get some help. If you didn't do well on the first test, you can do a retake on it. But again, if you come in and do a retake without coming and seeing me and getting some help on the things you missed, probably not going to do very well on the retake, but that is your option. Okay? So the more you are willing to do, the better off you are going to be in this class. Just so you know, ladies and gentlemen, please keep that in mind. So again, I gave you grade reports last week. I gave you your test back. I gave you all of those things, ladies and gentlemen. I gave you your grade reports, so you have those. So everything that you were supposed to be given, you should have. There you go. And again, last week, Friday, actually Thursday and Friday of last week, we did a lab activity. If you were not here Thursday and Friday, please open the lab activity. That's all you need to do is open it up right now. I will then take and I will put in an alternate assignment for you if you were not here. So I will put in an alternate assignment, but you need to open up the finding density lab activity or graphing to find density lab activity, because if you don't open it up, I can't put an alternate assignment in there for you. Once you open it up, I can go in, I can change the assignment to one where you don't have to have been here last week, Thursday or Friday, to complete it. So I need you to do that if you were not here on last week, Thursday and Friday. Just go in, open it up. I will check at the end of the day, and then I will put in the alternate assignment for you. It goes that way for any of you if you miss the entire lab. Now, if you missed last week, Thursday or Friday, but you were here one of the days, because remember we started at the end of class on Thursday, we finished it on Friday. If you miss one of the days, you can get the results from a lab partner. So they can fill you in on what the masses were, what the volumes were, things like that. I have no problem with that. But I will stress this to you, ladies and gentlemen. You are expected to work with a lab partner on your labs. What I am not expecting to find is the same spelling error on the same question in two different labs. Because that means you didn't work on the lab together. That means one of you shared your lab with the other. They copied and pasted their answers in, and that's not acceptable. Okay? Yes, I expect you to collaborate on your partner on the question. Hey, Jules, what do you think of this? What should we write down? Come up with an answer together, but I expect you to type them up individually. Okay? And if you're not here and you copy somebody's lab, okay, and I catch it, I'm going to give you a 0 on it. Okay? Do your own work. Yes, they should look similar. Yes, your answers may be almost identical to each other, but I doubt you are going to both misspell the same word at exactly the same point in two different labs. Okay? Questions? Okay. So, those should get turned in by the end of the hour today, ladies and gentlemen. If not, I'm going to start marking them late. Yes, Jules?
What if your lab partner never comes, or comes once in a week?
Then I would pick a different lab partner the next time you do a lab. I cannot control people's attendance. That's the one thing I cannot control. So if you're picking a lab partner who is gone all the time, you're going to be working solo. I try to make it so that you work in groups of 2. But again, if you want to work on your own thinking this person is going to show up, some labs I won't let you do that because there's just too much to do. Okay? But again, I'm sorry, but it's the one thing that I cannot control as a teacher. So, okay? All right. Any other questions? All right. Open up your EISN, ladies and gentlemen. Your electronic interactive science notebook. And I want you to get to, let's see, slide number 20, please. Okay. Now, yesterday in the video, you went through, hopefully you copied these notes down. Hopefully you have them into your EISN. There are 2 laws that are very important in chemistry and in science. Law of conservation of matter, law of conservation of energy. Laws are things that cannot be broken, ladies and gentlemen. A law is an irrefutable fact of nature. You cannot change that. These are 100% for sure. And the 2 laws, ladies and gentlemen, are almost identical to another. And they both say that in the case of the law of conservation of matter, matter cannot be created or destroyed. It can only be changed. And that is what happens during chemical reactions. And we will see that all year long in this class. We will take chemicals, we will put them together, they will change, and they will become something new, something different. Now, what has not changed is if I begin with 25 grams of this and 25 grams of that, at the end, I have 50 grams of new stuff that I have created. I still have the same amount of matter or the same mass. It is just rearranged in a different way. Now, the same is also true of energy. Energy cannot be created or destroyed. It can only be changed, and you are going to do that in an activity in just a few minutes. You are going to take potential energy and you are going to convert it into kinetic. You are going to do work and make it into kinetic energy. We can change things. What we can't do is change the amount of energy. From start to finish, it has to be the same. Okay? Now, some of the energy may go to places that we cannot recover. Some of the mass may go into places that is harder to recover. So, for example, if our reaction creates a gas, where do gases end up, ladies and gentlemen? Where do gases end up? In the atmosphere. We cannot recover them once they are in the atmosphere. So we either need to do the experiment so the gases cannot escape, or we need to understand that if gases go off into the atmosphere, we don't get to measure their mass anymore. Okay? That doesn't mean that we broke the law of conservation of mass. Okay? So the mass before a chemical reaction is equal to the mass after. The energy before a chemical reaction is equal to the energy after. Applies to chemical changes, applies to chemical or physical changes. And we will get into discussing what those are. Now, then we gave you a few definitions, ladies and gentlemen. Matter, anything that has mass and takes up space. Mass is the amount of matter a substance contains. Energy is the ability to do work. Doesn't mean you are actually having to do work, but it is the ability to do work. That is what energy allows us to do, work. Weight is the pull of gravity on an object. So on the last unit, we talked a little bit about mass and weight, because mass being one of the base units. Well, there is a difference between mass and weight, and the difference is the mass of an object never changes. Your mass is the same no matter where you are. Your weight can vary depending on where on Earth you are, or if you are on another planet. Because weight is dependent on gravity. Gravity is the force that attracts us to the center of the most massive object around, which is the Earth, ladies and gentlemen. Now, you could technically, or would technically, weigh less in an airplane than you do on Earth. Any idea why? Because you're further away from the Earth. Think of two magnets attracting one another, ladies and gentlemen. These magnets on the wall over here, on the metal post, are attracted to it. Now, if I pull that magnet away, is it going to go flying to that wall? Does that mean the magnetism shut off? No, it is still there. But now it is so far away that the force of magnetism is no longer the strongest force. The force of magnetism isn't as strong as the force of gravity, and gravity will make this object fall to the ground. This object is now defying gravity. Why? Because the force of the magnetism between it and the metal are stronger than the force of gravity trying to pull it down. Strongest force always wins. Okay? Gravity is a force of attraction between any two objects that have mass. You have mass. Therefore, you create your own gravity. It is just that on Earth, that gravity goes unnoticed. Why? You are not the most massive object around. The Earth is. Okay? If you could go into outer space and be alone, let's not say alone. Let's say you're with somebody. You two would be attracted to each other. Not physically. Okay? Well, yes, physically. Maybe not emotionally. But you would be attracted to each other physically because you would both generate gravity, and objects with gravity would want to come together. Assuming you were the most massive objects around. Okay? A force is a push or a pull. Very simple. You push something, you pull something, that's a force. Just like gravity is a force. Questions? Now, there are two kinds of energy. There is potential energy and there is kinetic energy. Potential energy is stored energy, and there are three ways to store it. Number one, you could store energy by height. These boxes up here all have potential energy because if I move them away from the shelf, they will fall to the ground. That is potential energy. Any object that is above the Earth's surface has potential energy. You could also have potential energy based on deformation. A ball, when it is bounced, deforms when it hits the surface. So if you take a ball, either one that has air in it or one that is a rubber ball, when it hits the table, it literally squeezes down, stores up energy, and then releases it to come back up. That deforming is storing energy. Potential, the same as those boxes up there. Okay? So things like springs, any kind of a ball, as far as any, like a soccer ball, a baseball, things like that. Even, ladies and gentlemen, a rubber band. You can deform it. You can stretch it out. When you let it go, it's going to go back to its shape. Springs, the same way. Okay? And then there is also chemical potential energy. Energy from the chemicals inside of things. In other words, Those books on the table, I could burn them and I could release that chemical potential energy. Okay? What's that? No? Okay, good. Now, I will not make you use the formula for potential energy. Just wanted to show you what it is. Potential energy is equal to the mass of an object times gravity times its height. That means, of these three, which two can change? Which two could easily change?
Mass and height.
Mass and height. We cannot change the gravity unless we take this object to another planet. Okay? On Earth, the gravity is going to be what it is. Does not change. You go to the moon, you will change the amount of gravity on that object because the moon has 1/6 the mass of Earth, so it has 1/6 the gravity. If you weigh 120 pounds on Earth, on the moon you weigh 20 pounds. Best weight loss program ever. Okay? If you weigh 180 pounds on Earth, you weigh 30 pounds on the moon. Now, the bad news is your mass doesn't change on the moon. How much matter makes you up doesn't change there or here. Okay? And it's measured in a unit called joules. Kinetic energy is energy of something has because of its motion. If it's moving, it has kinetic energy. Depends on mass and what we call velocity. What is velocity? Speed. Speed and technically direction. Speed and direction. Kinetic energy is 1/2 the mass of an object times its velocity squared. Again, not going to make you use those formulas. Take physics in a year, you'll get to use them all the time. Not in here. Both measured in joules. Why? Because any kind of energy can be measured in joules. Because energy is energy, I don't care what kind. Potential can become kinetic. Kinetic can become potential. Chemical energy can become other kinds of energy. Doesn't matter. All measured in joules. Questions? Wonderful. So that brings us to this, ladies and gentlemen. Please get to this slide, and this is what you're going to go do in just a couple of minutes. So, all right. We're going to look at kinetic energy, and kinetic energy has two variables, mass and velocity. I have 3 books up here. Look at them and tell me, in terms of mass and velocity, what's different about them.
The one on the left is the biggest, has the most mass.
This has the most mass. Second, third. 3 different masses. So when we use these books, we are going to change the variable of mass. That is what we are doing right here. This part. We are going to try to leave speed constant, velocity, and we are going to try to change the mass of these 3 books, which we do by selecting a different book. The heavy mass is obviously this one, the CRC handbook. This is the one that represents the heavy mass. This represents the medium mass. This represents the light mass, or the lowest mass. Fair enough? Okay. All right. Abby, come stand up here at that side of the table. Please. Okay? So, 3 different objects are pushed across the lab station at the same speed. Record how difficult it was to stop the object. Now, I don't care if you want to rank them with a number. This one was the most difficult, second most difficult, third most difficult. Or if you just want to put the hardest to stop, the easiest to stop, and somewhere in the middle. Abby is going to be at one side of the table. I'm going to be at the other. You're going to do this in the back. Please do not wipe out my $1,000 balances with a book while you are doing this. One partner on one side, one partner on the other. I'm going to try to push this book at Abby. Actually, let's start with the lightest one. Ready? Okay. She will now judge how hard it was for her to stop. Slide that to the side. Now, the hard part of this activity is this one. I'm now going to try to push this book with the same velocity that I did the last one. Now, since the book is heavier, what does that mean for me? I'm going to have to push it harder. You ready? Was that one harder or easier to stop than the first? Okay, slide it off to the side. And now you're going to do the third one, and you're going to send it across at your partner. They're going to judge how hard it is to stop. You are going to judge how difficult it is to push. And you are going to rank them. Was the heavy object, thank you, Abby. Was the heavy object the hardest to stop, the easiest to stop, or somewhere in the middle? That's all you're putting in these yellow boxes. Does anyone have any question on that? Part 2 of kinetic energy. Now we are going to change the speed, but we are going to leave the mass constant. That means you need to pick one of these 3 objects, and I don't care which one you pick. You want to pick this one, that's fine, but then on this line, you put heavy mass. You want to pick this one, that's fine, but then on the line, you put medium mass. You want to pick this one, you put on the line small mass. Okay? Ray, come on up here real quick. So now, I use one book. That is it. Same thing. Going to push the book across the table to Ray. But now I'm going to push it slowly. Now I'm going to push it faster. And now I'm going to push it really. Ray was nervous. Go ahead. You can sit down, Ray. Thank you very much. You're going to move it faster on the 3rd time. And again, you're going to judge which one was the easiest to stop, which one was the hardest. I didn't say this was not a no-brainer lab activity. It should be a no-brainer lab activity for you. Okay? So then over here, when we increase the mass, this one, the kinetic energy, did it increase or decrease? And I know this because, well, if something has more energy, do you think it's easier or harder to stop? Harder. Good. So, which one was the hardest to stop? I don't know yet. You haven't done the lab. Might be. Who knows? Maybe physics works backwards to what we think, and actually the lightest was the hardest to stop. I don't know. Do the lab, find out. But in here, you are going to tell me, if we increase the mass, what do you think happens to the kinetic energy? And then how do you know? Give you a hint. Here's how you know. Which one was the hardest to stop? Down here, when we increase the velocity, these 3. The kinetic energy, did it increase or decrease? And you know this because, why? Which one was the easiest to stop? Which one was the hardest? Questions? Okay. That's kinetic energy. You've got one more slide to do right afterwards. Slide number 25. Now we are going to deal with potential energy. 3 things affect potential energy. What are they? Okay, it's height. Height, 1. What else affects potential energy? Mass. The 3rd thing that affects potential energy. The one that we cannot change. Gravity. But we are going to test how mass and how height affect potential energy. So again, the first time we're going to leave the height constant, but we are going to variable the mass. We are going to variable the mass. Or Theo, come stand up here. So you're going to take the heavy mass. Theo, put your hands out in front of you. Do not drop this, Theo. Understand?
I'll try my best.
Oh, no, you're going to do, right?
Yeah, I will.
You're not going to drop it. So I'm going to hold it up. I'm going to drop it. You ready?
Nope. Okay, yeah, no.
He's going to catch it. We're then going to do the exact same thing with the other 2. We won't do that. We were 1 for 1. We're going to stop while we're ahead. Theo, thank you very much. Hold it at the same height. Drop it again. Different mass. And then finally, the 3rd mass. And then I want you to judge which one was the easiest to stop, medium stop, hardest to stop. Now this one bends and they'll be like, well, this one was the hardest to stop because it bent and it went through my head. Of how much force or how much work you have to do to stop it, that's what I want you to judge. Okay? Question. Then we're going to variable the height now. So now we're going to variable the height. We're going to change the height. We're going to pick one of these three objects. One of these three objects I'm going to pick. So I'm going to pick the medium book. Okay, Giselle, come on up here. Hurry up. Okay. Hands out. Don't drop it. You ready?
Mm-hmm.
Good. Stay here. Come back here.
Oh no.
Let's try this again. You ready? Okay, good. Oh! Low height. Ready? Sure? Don't look at me. Look at the book. Ready? Good? Okay, good. Where are you going?
Oh shit.
We need height now.
Okay.
Now, there are steps that can get you up onto that table in the middle, ladies and gentlemen, if you want to do it there. I don't have steps for you on the side. But don't kick over my balances. So now we would do... Don't panic.
Okay.
Ready?
Yeah.
I'm not going to do that to you. Which one is the easiest to stop? Which one is medium? Which one is the hardest to stop? Question. Again, the last column. We're talking about potential energy now. How did mass affect potential energy? Which of these books was the easiest one to stop with potential energy? From the same height. Was it the lightest? Was it the heaviest? Was it the medium? Then we're going to pick one book. Was it easiest to stop low, medium, or high? Questions. You need to answer those two questions over on the side and finish them up. All right, so how long do you need? What, 6 minutes?
20.
No.
The rest of the hour.
No.
15.
We'll compromise and give you 13 minutes. Go to work. Go to work. Well, 6 and 20, the compromise is 13.
Okay.
It doesn't take long. Find a partner, get to work.
Hello.
You may want to move your computer screens off to the side so you don't wipe them out. Put them near my balances so that way you protect my balances. Sorry. Go ahead. One on one side, one on the other. If some people want to start on the potential energy first, you're welcome to. But you need to share the books at your station. Ray, what can I do for you? Yeah, that'd be fine. Yes. Please, Ray, because I think we're at an odd number today. So. Now, let's not pick lab partners and then insult them because they're thinking about things. It's okay to think about things. Now remember, it's really hard to get them at the same speed. Stop! You guys shut the door. You take that stop. You need to pull it harder so they can stop. Now try to do that same speed with the different one. Even though here you only have to pull it. You gotta kind of make sure it gets there so that they can stop its complete. Okay? What are you doing over there with the book? gotta give it to your partner. I don't know how you're ready for the last one. So long as you understand what's it when you put it. I think it's easy. Oh, wait, never mind. That's your computer hates you. I don't even have to. Go get to work. Don't hit him on the head, Elsa. It doesn't mean you have to dig low. The height you probably come from is lower than I. Now we gotta get down to that level. That's what we start. Mississippi Hall 3 books at your station. What's that? Well, again, see, that's the part about physics. Physics is real easy. You know 90% of physics. If I throw a bullet in here for your life,
No.
if I shoot it out of the gun, are you going,
Yeah.
why? What's the difference?
If it's not, you don't make it.
No. It's a bullet.
Yeah.
But it's a bullet, whether I throw it, it's sure. Okay, so you know that the more what, the more they get penetrated. The less they get, the more. Okay? So if somebody takes a bowling ball and their head and drops it, now they go up on the top of the tall building and drop it to death. A bowling ball.
I think you do something nice and hello.
Because they need three objects that are supposed to be the same size. They're not bad. All right, they have three colors that are the same size. I wouldn't want light one. Well, congratulations. Actually, it's going to push. The actual hard part of this slide is yeah, right. I only need 12 minutes, and I can take one more minute. Yes.
So we have to use this
Right. On all parts. What? After energy that was stored, the question is, so all of that energy. So at low height, you get a lot of energy. Medium height, high height most of our life. Why? Here it has the most potential. Absolutely. Absolutely. All right. Gonna give you a little secret, ladies and gentlemen. You know 90% of physics. You really do. A lot of physics is common sense. And Jules was yelling at me because, why did you have something? Whatever. I stopped listening after she started talking. But anyway. Okay. You're standing under a coconut tree. A leaf falls. Do you fear for your life? A coconut falls. Do you fear for your life? And maybe. You know how high coconut trees are? You know how many people die every year from being hit by coconuts? More than die from shark attacks. More. Why? Well, the coconut and the leaf are at the same height. Why does the coconut hurt more? More mass. So the height isn't the big determining factor. There the mass is. Well, what we should have learned in our lab is that if we take the heavier book and drop it even from the same height, it should be harder to stop than the lighter book. Now, as Stephanie brought up a great point. Well, when you're stopping it, what kind of energy is it? When we drop the book and you stop it, what kind of energy does it have? What's the book doing? Moving. What kind of energy is that? Where did it get the kinetic from? From the potential that we had stored up into it. So again, remember the law of conservation of energy? Energy cannot be created or destroyed, but it can be changed. You hold the book up, it has potential. You let it go, it starts getting kinetic. Okay? Little height, little kinetic. Medium height, medium kinetic. Tall height, a lot of kinetic. Why? A lot of potential, medium potential, low potential. Okay? Low potential. All right? And if you think about the one where you shoved it across the table, okay, the one that was hardest to stop was also the one that was hardest to do what? Hardest to push. Because you have to put the energy in to get it moving. Somebody else has to put the energy into stopping it. The one who puts the more energy you put in, the faster it's going to move, the harder it's going to be to stop. Okay? That means we're depending on how fast the object is moving. But a light object moving at a low speed. How many of you have ever heard that if they dropped a penny off of the Sears Tower or off of a very tall building, it would kill you if it hit you in the head, right? It will not. Why? No, there's just not enough mass there. If someone throws a feather at you really hard, it's still not going to hurt.
It's probably not even touch you.
It may. But if it does, it's not going to hurt. Why? Because of its very small mass, even if it is moving incredibly fast, a really big number times a really little number doesn't give you much of a number. Right? So again, now somebody stands on a tall building and drops a bowling ball. Look out! 16 pounds, very heavy. Going to make a crater coming out of you on the other side. That's not a good thing. Okay? So again, kinetic energy, potential energy, they both depend on mass. How heavy the object is. But kinetic, because it has to be moving, also depends on how fast it's moving. The faster it's moving, the harder it is to stop. Someone throws a bullet at you, you're not worried. Somebody fires it out of a gun, you're in trouble. Then velocity is important too, because are they aiming at you or are they aiming somewhere else? Direction and speed matter. Okay? For potential, how high is the object falling from? But again, even if it's falling from a really high height, if it's not very massive, it's not going to hurt. Okay? Okay? Questions? All right, let's get to the last slide then. Because what you just did is learn about relationships, ladies and gentlemen. So let's talk about the relationships that you just learned about.
Mr. Brent,
Yes.
only 10 people die from shark attacks a year.
Yep.
And 150 die from falling buildings.
Didn't I just say that? More people die from coconuts falling out of trees than being bitten or attacked by a shark.
Yes, but also like more people are killed by like elephants and like crocodiles and bees than they are killed by sharks.
But sharks get a bad name. And you know the easiest way to not get attacked by a shark?
Don't go in the water.
Don't go into water. Last time you see a shark walking down the street attacking somebody, tell me when it was. Never. Never. Okay. Velocity, if it increases, but mass is held constant, what will kinetic energy do? Okay, so what I want you to do is take that arrow that points up and put it here. Because now we have a sentence basically. Velocity increases, mass is constant, kinetic energy increases. So if velocity decreases and mass is held constant, what will happen to kinetic energy? It'll decrease. Okay, so which one of these relationships is this? Good. So erase the one that says inverse. Just get it off your slide. And that's all that should look like. Which means in terms of velocity and kinetic energy, they are a direct relationship. If one goes up, the other one will go up. If one goes down, the other one will go down. Questions? Good. Let's get to the next slide. Same formula, but now we're holding velocity constant and we're changing the mass. So again, when we use the heavier book at a constant velocity, what happened to kinetic energy? Increased. So take that one arrow and move it over. What that means is now you can take the other arrow and put it where mass decreases. Constant velocity, what happens to kinetic energy? Okay, what do you notice about the two arrows in the top line? Why? Okay, they're both going in the same direction. What about the bottom line? They're still both going in the same direction. That is the definition of a direct relationship. When two variables are changing in the same direction, both going up, both going down, doesn't matter. Okay? Still both direct relationships. Okay? So now we're going to talk potential. Okay? So if we increase the mass, the heavier book, what happened to the potential energy? Don't make shining answer, Mo. Come on, somebody else help. All right, I'll call on you. Finley, what happened to potential energy when mass went up? Goes up. Good, thank you. What happened to potential energy when mass decreased, Sam? Went down. Are you guys allergic to talking or what? Okay. Zach, what kind of relationship? He's got to talk to me now because you can't just go for this one. Direct. Very good. So erase that inverse part. Both arrows still going up, both arrows still going down. All right. What about now if we talk about height? Okay. Albert, the height increases. What happens to potential energy? It increases. Thank you for talking to me. The height goes down. What happens to kinetic or potential energy, Evelyn? Sorry. The height goes down. What happens to potential energy? It decreases. Good. What kind of a relationship is this? What kind of a relationship is this, Adriana? This is a direct. Very good. They're both, all four of these were direct relationships, ladies and gentlemen. Mass and kinetic energy, velocity and kinetic energy. Mass and potential energy, height and potential energy. All direct relationships. You increase any of them, you increase the other. Questions? Okay. So, you have 1 minute. Describe to me the kinetic and potential energy of that book right there, right now. Go. Type it in your box. Make sure you clarify. The kinetic energy of the book is this, and why. The potential energy of the book is this, and why. By the way, there are multiple acceptable answers. You don't need to go crazy. You don't need to type in a 4-paragraph essay. The book has this kinetic energy, this potential energy, and why. Alicio, kinetic energy.
Has a lot of kinetic energy because it's heavy.
Okay, but to have kinetic energy, the book needs to be what? Is the book moving?
No,
So what should our answer be?
it has no kinetic
Because the book's not moving, right? Okay? Now, Stephanie, potential energy.
It has a lot
Why?
because it's not moving.
Okay, but that's potential energy means that the book must be able to do what?
Fall.
Can this book fall from where it's at? So what kind of potential energy does it have? 0. So right now, and you're right, okay? You're right about the mass of the book. I totally agree. But to have kinetic energy, you must be moving. To have potential energy, you have to be able to fall. So right now, can that book do either one of those things, or is doing either one of those things? So therefore, it has no kinetic and no potential. A student says they can prove that that handbook sitting on the floor has both kinetic and potential energy. Since this is possible, what is the student's explanation for both forms of energy in the book sitting on the floor? Can anybody give me one of the two? How a book that is not moving on the floor and cannot fall could still have kinetic or potential energy? Nope, we're not going to go there. But that, I would at least accept that. You could say the floor could open up, and because we're on the second floor, it could fall down. They're reasonable, but not what I was thinking. Anybody else? Okay, but then again, I'm then adding the energy to it. And I agree. I could pick it up, and I could give it potential energy. I could push it, and I could give it kinetic energy. They say the way the book is right now, it has both kinetic and potential energy. Anybody have an explanation for it? And they are right. What? What about it? Okay, it is, but it's not pulling it down right now, right? It has no height. Potential energy, you need height to be able to fall, unless you're talking about other types of potential energy. There were 3 that I discussed with you. What was one of the other 2 types of potential energy? Yeah, but I really can't deform that book, can I? But it could do what to that book? Told you we could do it to these books earlier. Thank you. These books have chemical potential energy because they could be burned. That book, even though it's not moving down there, has chemical potential energy because you could burn the pages of it and the book itself. Okay, so how does it have kinetic if it's sitting on the ground, not moving? And you can't say, well, it could start moving. That book is not walking away on its own. But right now, it actually does have kinetic energy. Anybody? The what? You're close. What? The particles inside the book are actually still moving. The book is not. The particles inside it are. So therefore, because the particles inside it are moving, technically the book has kinetic energy. Technically, the book could still be burned, giving it chemical potential energy. Very good. Very good, ladies and gentlemen. So I would ask you if you guys missed me yesterday, but I really don't think you'd tell me honestly anyway. So did you, Jules?
Yeah.
So okay. Next. Good. Anyone need a little more time? Come on. Where's my cursor? Oh, let's try turning on. Okay. An elephant and a mouse run a race, and they are tied. Explain how their kinetic energies compare. An elephant and a mouse run a race, and they are tied. Now, let me ask you this question before we go any further. Any two objects that run a race and finish tied, what does that mean about them? They finish the same. Now, think in terms of kinetic energy. What does that mean is the same for both objects? Yes, very good. Their velocity. So by saying they're running a race and they finish tied, what we're saying is they have the same velocity, because otherwise they couldn't finish tied, correct? Okay, so how do their kinetic energies compare now? And I hope I've used a good enough example that it's pretty obvious what I'm trying to get you to think about. What is the difference between a mouse and an elephant? And please only think in terms of kinetic energy. Don't tell me one has bigger feet than the other. Okay, one has a longer stride than the other. I don't care. I care about something that would affect kinetic energy. Remember, ladies and gentlemen, these are your notes. What you're writing down, you may come back and look at, and if you write down the wrong answer, leave it. Well, that's up to you. But all right, Karina, how do their kinetic energies compare to each other? Perfect, absolutely. For those who didn't hear what she said, the elephant has more because it has a bigger mass. The elephant will have a lot more kinetic energy than the mouse. Both moving at the same speed, elephant has a larger mass, therefore it has to have more kinetic energy. Questions? Okay, a baby and an NFL lineman now run a race. They finish with the same kinetic energy. Who wins the race and why? What? Why?
Because the baby can't even crawl.
How do we know the baby? So what, you're saying all babies can't crawl?
It doesn't say the age.
You're right, so don't be thinking it's right out of the womb.
It's not saying it's not.
The baby wouldn't be in the race if it couldn't move. The baby runs the race and wins. Actually, let me rephrase that. I'm sorry. They both finish with the same kinetic energy. Who wins and why? Why?
Because he's bigger than the baby.
So when you say bigger, think in terms of kinetic energy. What's the only thing that would affect this kinetic energy? He's more massive. So you're saying the lineman wins because he has more mass and therefore he will have more what? But they don't have more kinetic energy. He has the same as the baby. And you're right, the baby has a smaller mass. So how could an object with a little bit of mass and an object with a large mass have the same kinetic energy?
Oh, the lineman's going really slow.
The lineman must be going really slow. And the baby must be going fast. Because the only way they can have the same kinetic energy without the same mass is they have different velocities, correct? The baby's velocity has to be more because its mass is less, because kinetic energy is equal to 1/2 mv squared. So the only way two objects can have the same kinetic energy if they have different masses is they have to be moving at different speeds. And the lighter one always has to move faster. The lighter one has to move faster. The baby wins the race because the lighter object must move faster. Don't give me the, hey, that lineman, he might be old and like bad knees and can barely move. That baby kicks its butt. Kicks its butt. Questions?
See that.
Well, what does NFL stand for? Who said that? That's the No Fun League. He's a linebacker in the No Fun League. These guys are old. They just go play every once in a while on weekends. Oh, sorry. Don't lose yourself in my silly question. Okay, questions? No? We're good? Okay. Two roller coasters are stopped at the top of its tallest hill at the same time. So two dual racing roller coasters are at the top of the same hill. Stopped. How is it possible they don't have the same potential energy? They're at the exact same height. How is it possible they do not have the same potential energy?
One has more cards, maybe heavy.
Okay, I don't care how you say it. One has more carts, one has more heavier people in it. Potential energy depends on mass. Okay? These boxes up here do not all have the same potential energy because some of them have stuff in them. This has goggles in it. These are empty. Two objects at the same height, the heavier one will have more potential energy. The heavier one will have more potential energy. How is it possible for a bowling ball and a golf ball to have the same potential energy? How is that possible?
Volleyball is higher up.
Volleyball's low.
Thank you. You had the right idea. But the heavier object would need to be what?
I was just making sure she was awake. Do we have one of those staplers that staples like a little clip?
Yeah, it's called your stapler, and you just go right near the
But
edge.
it's not, it doesn't have enough space.
We don't. I'm sorry. Sorry.
Well, you're
Sorry.
What happens when I decide I'm gonna change?
There. Don't change. We like you just the way you are. So you have the right idea, Kevin. But the heavier object needs to be closer to the ground. The lighter object needs to be higher up. That is the only way they can have the same potential energy. Okay? Just like the baby and the lineman needs to be moving slower. The baby needs to be moving faster to have the same kinetic energy. Kinetic energy always depends on mass and velocity. Potential energy depends on mass and height. Questions? Okay, so we're going to get through this real quick. Give me an example of something with only kinetic energy. Only kinetic energy.
Car moving.
More specific.
Car moving on the ground.
Okay, car moving on the ground, because I was thinking of a car going over a bridge. Car going over a bridge, does it have kinetic? Why? Moving. Going over a bridge, though, it also would have what?
Potential.
Why?
Because over some.
Because it could fall down, correct? Okay. News this morning, some person drove their car out of a 4-story parking garage. It's now sitting against the tree in the garage with a person inside it. Okay? Potential energy there. Okay? Potential energy there because it could fall. Okay? Give me something with potential only, no kinetic. Box on a shelf. Box on a shelf. Bird sitting on a wire. To have potential, it needs to have what? Come on. Height. To have no kinetic, it needs to be what?
Same still.
Not moving. Not moving. Both kinetic and potential. So the object needs to be above ground and moving. Give me something. No. I was on one. When it's sitting there on the runway,
Oh, an airplane.
not moving, no potential energy. Airplane flying through the air, yes. What else? Come on. What else?
Car on the bridge.
Car on the bridge. Moving car across a bridge. A soccer ball kicked in the air. A football thrown in the air. Any object moving in the air somehow has both. Right? Now, no kinetic, no potential. Means it can't be what? Can't be moving and can't have any. How? How do you get potential?
Can be above
Can't be above
the ground.
the ground. What?
The floor.
A rock where? Sitting on the ground. A rock sitting on the ground. A book sitting on the classroom floor. Your desk in this room. Not moving. Not above the ground. Neither one. Okay. So, please remember, all of the objects that you described all had what in common that affects kinetic and potential energy? That doesn't affect kinetic. Mass. They all had a mass. That affects kinetic and potential. For kinetic, the object has to be moving. For potential, the object must be above the ground. If you want both, it needs to be moving and above the ground. If you want neither, it cannot be moving and it cannot be able to fall. Cannot be moving, cannot be able to fall. Okay? Questions? All right. Tomorrow then, ladies and gentlemen, we will talk about the KMT portion that the substitute should have discussed with you. Okay? Questions, ladies and gentlemen? Wonderful, wonderful, wonderful. So, okay, show of hands. Who liked the start of the video yesterday? See, I knew I'd get a few of you. You thought you were getting no good morning because I wasn't here. I did that every day when we did COVID videos. Every day I recorded my good morning and put it out on my COVID videos when we were all at home studying chemistry and other things. So,